Hello, this should be the last of these types of lessons, as I'm feeling a little bit better and things are going well, which is good, but I'm not allowed back in until next Monday, so the doctor has signed me off. Anyway, less of me and my moans about bugs picking up from college, and let's get on with it. So today we've got a starter question for you here. It says obtain the first three non-zero terms of the expansion in the ascending power of x. So here I'm looking for Maclaurin series. Hopefully you've been enjoying Maclaurin series with Glenda, or maybe even you met a bit of L'Hopital. Anyway, but we want you to use Maclaurin series on the first two, expand them, and then hence find the limit as it tends to 0. So have a go, pause this video and have a little go at that. So it's using those Maclaurin series. You'll need your formula booklet. Maybe unpaused now. So here comes a bit of the answers. So replace x in Maclaurin series of the expansion for e to the x by minus x. The first three terms of e to the minus x will be those, and therefore x to the power 3 times that gives us that. The sign 2x, just put 2x where you see an x in the formula booklet, and you get that. So that's part A done. And then part B, hence find the limit as x tends to 0. So we had to put in the expansion bits from part A. Look at the bottom there, something's going to disappear. And then we're left with both top and bottom, and the 2x disappears, top and bottom both being x to the power 3 and higher terms of x. So we divide both top and bottom by x to the power 3, and then that would leave us with the coefficients 1, x to the 3 here, and there were plus 4 over 3, x to the 3's there, so it leaves us with 1 over 4 over 3. So as x tends to 0, all these other terms lead to 0. It tends to 1 over 4 over x, which is 3 over x. Sorry about the coughing. Hopefully you manage that one, or understand it if you don't. Right, L'Hopital was the last thing you did with Glenda, just finishing off lesson 2 here. It was an alternative to the other chap, Maclaurin. That's a pen. Right, an alternative. You've seen this slide before, and it's called L'Hopital, or the hospital rule. Right, anyway, it only is a method for finding limits of the form 0 over 0 or infinity over infinity. Basically, L'Hopital says that the limit of a function f of x over g of x is the same as the limit of its derivative of f dash of x and f g dash of x. The limits are the same, but if and only if the f of x as limit, as x tends to wherever it's going to, is 0, and the g of x limit is 0, or they're both tending towards either positive or negative infinity. And that is a step we must show we're doing before we try and use L'Hopital. And obviously provided the differentiation exists of the functions. Okay, you got up to example 7. Use L'Hopital's rule to find this thing. So first we check that the limit is in the correct form to use L'Hopital. In other words, the top, as x tends to infinity, must tend to, well, let's see what it tends to. As x tends to infinity in here, e, 2 lots of e to the infinity is basically tending towards infinity. And as x tends to infinity, infinity to the power 3 is again infinity. So here we've got it of the form infinity over infinity, and therefore we can use L'Hopital. So it's suitable for L'Hopital because it's in that form. Right, so we need to differentiate because L'Hopital said the limit of that is the same as the limit of the differential of both functions. So if you differentiate the top, we'll still get 2e to the x. If I differentiate the bottom, I'll get 3x squared. Okay, where to stop, because that's not telling us much if you put infinity in there, is it? Because we get infinity over infinity again. So now that's of the form infinity over infinity, so we need to use L'Hopital again, because at the moment it's still in that form. So differentiating again, we'll still get 2e to the x, but I'll now get 6x. Again, as x tends to infinity, that's of the form infinity over infinity. So I'll need to do L'Hopital yet again. And then that's going to give me 2e to the x over this time just 6. Which is now, if we were to put in our x, we'd end up, that's the same as giving us what's equal to, that be infinity over 6, which is basically infinity. So therefore the limit of that thing is tending towards infinity. Okay, so that's the answer, and yeah, that's about it, isn't it? Oh, there's the picture, so you can see what's happening here. As x tends to infinity, I know it's only 6 there, and 7, it's going off, up there, and it would go on up forever. Right. Okay, here's one for you. It says use L'Hopital's rule to find this. But alarm bell should be going off straight away here. That's not a quotient. And L'Hopital's rule only works for a quotient where we've got a function of x divided by a function of x. So when you're having a go at this one, you'll have to change it a little to be the limit as x tends to 0 of, you can't change ln x, but you can write x on the top as 1 over x on the bottom, because if you popped it to the top it'd come back to x, wouldn't it? So there's your f of x, there's your g of x. Give this one a go. Remember, first show it's suitable for L'Hopital by doing the top, seeing what that tends to, and the bottom what it tends to. needs to tend to infinity over infinity or 0 over 0. Pause if it's taking you a while. So if you're ready, here comes the answer. So if you're looking at it, there was where we wrote it, ln x over 1 over x. 1 over x can be written as x to minus 1. So when you differentiate x to minus 1, you get x to minus 2 minus. And that's gone to 1 over x. That can be rewritten, can't it, as 1 over x divided by 1 over x to the 2, which can be rewritten as x to the minus 1 divided by negative x to minus 2. Subtract your powers, so that gives us the limit of the minus x to the 1, and that is just minus 1 over x, and as x is 0, that tends to 0. Yeah, obviously it doesn't, it's a positive one, yeah. X tends to 0, you put that in, minus 0 is 0, isn't it? Right. Another one. Pause the video and have a go. Probably now unpause if you're ready. See what the limit has gone to. Hopefully you got them both to 0. Oh no, you didn't. Ah, this was a con, wasn't it, if you noticed? Real bad one, this one. That first limit is going towards 1 to 1, 0, isn't it? And this one, 0 plus 1 is 1. So it wasn't in the form 0 over 0. So stop. L'Hopital was not suitable. What on earth could you do? Well, the only other thing that we've learnt about is Maclaurin. Yes, Maclaurin. Thank goodness for him. So you can use your Maclaurin series of e to the x and pop that in and then have a look. So either pause again and finish it off, or look what we've done here. I've put in e to the x from the formula booklet. Take 1 over x plus 1. So that cancels down, the 1's disappear, don't they? And you're left with this thing. And if you put x is 0 in now, all the top lot would be 0. And the bottom's just a 1, and 0 divided by 1 is 0, so that's tending to 0. I wonder if you got that one. So here's a rule. There were two rules. One you proved with Maclaurin, and this one we're going to prove with L'Hopital. You first look at it a bit like the last example, but last. We need to write it as a quotient first before we can try and look at L'Hopital. So we can write that as ln x over x to the negative k. Now to check that both will go to either infinity or 0. Now the limit, so check, little check, we can use L'Hopital. So that would be limit as x tends to 0 of ln x. If you know the graph of that one, that's that one, isn't it? So as x is tending to 0, it's tending to negative infinity. So that's going towards, it's going towards infinity. And the limit as x tends to 0 of x to the minus k, which will be the same as the limit of x tends to 0 of 1 over x to the k. Right, a very small number to a big power is still going to, well, any power is still going to be very, 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 very small. So 1 divided by a very, 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 very small number is going to be infinity. So we've got our answer going to an infinity over infinity, so we can use L'Hopital. Right, so it says, L'Hopital says, the limit oops, what are you doing now? I'm doing the wrong thing. ln x over x to the minus k will be the same as if we differentiate both. So that's going to give me limit of 1 over x, and this one differentiate x to the minus k. I'm going to bring the minus k down onto, and then x to the minus k, and you take 1 off it as well. Right, can we rewrite that? Right, that's going to be like 1 over x divided by, if I write that divided by, because that's a negative, so we've got that k there is not to any power, so that's dividing by negative k, and if I drop those to the bottom there, they become positive powers, so that's x to the k plus 1. So that's the same as that, which is the same as, we divide fractions, we flip the second one and change it to a times. So now x divided by x plus 1 just give me x to the k on the top. So that's the limit of over minus k on the bottom. Right, now as we put x is 0 in there, that will give me basically 0 over minus k, which is 0. So we've proved it. QED. Lovely. Okay, last one for you to have a go at on your whiteboard with the same idea. Again, it's not a quotient, so you're going to have to change that to ln x over something that's not tan pi theta over 2. What's 1 over tan? I wonder. I hope you don't. Right, so have a go using cot and see what you make of that one. Pause the video. . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . . wonder how many people pause the video. Hope you're doing it. Anyway, right, it's unpaused now, I take it. So here is the answers. So first we should have checked that the limit as x tends to 1 would be 0. Oops, is it going to come up? Oh, it's not coming up. So that was 0 if you put 1 in there. And let's hope if I put pi by 2 of cough, hopefully that's going to 0 as well. So it was in the form of 0 over 0, so it was suitable for L'Hopital. And then you differentiate at the top and the bottom. You got 1 over x, and cot goes to cos x squared. And then if you put 1 into that, that actually gives you 1 over pi over 2, which, well, when you do it, it comes to this and this. Right, that was end of Glenda's lesson. So you'll find, I think that exercise will be on your homework for this week. So let's see what's new this week, on this Friday. So I've got the last lesson of these, which is improper integration. It's a bit easier probably than the rest. Maybe a little strange to 1 or 2 of you, but it's not hard. So let's whiz through this. It says an integral where, what is an improper integral? Well, an improper integral is one where one limit is undefined, both limits are undefined, or some point in between is undefined. A limit can be undefined if it is equal to infinity or minus infinity, or it is an asymptote of the graph. A sketch of the curve can sometimes be helpful to decide. Right, these 3 integrals are improper. Can you explain why? Well, the first one, it's obvious. One of the limits is infinity. So it's undefined at 1 over infinity squared. So it's improper integral because one of the limits is infinity. That would be the reason. The next one, neither of the limits are infinity. So is there a problem with the graph at some point? If you put 0 in there, 1 divided by 0, oh dear. That would give us another point that's sort of undefined at x is 0, it's an asymptote. And the last one looks to be no problem putting 1 and minus 1 in. However, if you know what that graph looks like, oops, do I? It's that one, isn't it? So if you're trying to integrate that between 1 and minus 1, there is a part in the middle when x is 0 where this graph does not exist. It's improper because again it's undefined at x is 0, and that's in the limits, between the limits 1 to minus 1. So improper or not, if you can't decide, sketch on the calculator and see. Just give you 2 minutes to have a go at that. Is that 2 minutes? I don't think it is, but I'm starting. So this graph, obviously, if you can't decide if it's, well, it is obviously because one of the limits is, but that's the thing. That's the graph, and you can see the area of that will be getting bigger and bigger and bigger and bigger and bigger and bigger and bigger. But it's improper anyway, because one of the limits is infinity. We couldn't work it out. This one, oh, let's go to this one first. 1 over x. If you're struggling with that, the 1 over x graph, 1 over x graph would look a bit like this. And there has to be integrated between 0 and 1. So there's a problem again at the 0. Put 0 in, it's undefined, and therefore it's improper. This one, it's a similar graph, you plot it on your thing, but the asymptotes now at x is -1. And so your graph will look a bit like this. And therefore integrating it between 0 and 1, there is absolutely no problem whatsoever. So that's actually a proper integral. It's not improper. You can actually work that out and get a number spot on. And this one, this would have an asymptote at 2. Again, it's a reciprocal graph. Oops, weird. So trying to find the integration between 1 and 3 would include the point at 2 where it's undefined. So it's undefined at 2. It's improper. Defined or not. Sometimes an improper integral can actually be calculated and sometimes not. It is very hard to tell before you start, but what do you reckon, often helps. When trying to find the integral value, we replace the limit that the function is not defined at with a variable. Work out the value of the integral in terms of the variable, and then look at what happens as the value of the variable tends to the original value. That sounds awful, but it's really easy. So let's have a go at this first question. Find the integral of this thing. So replace this is obviously the problem, the infinity. So replace that with a letter. I always choose P. Don't know why, I like P. So replace the infinity with a P, and then we go for it. Right, that's the same as trying to integrate x to the -2. So that's add 1 to the power, divide by the new power. Rewrite it before I put any of those limits in. X to the -1 wants to drop to the bottom, so it's the same as -1 over x. When I've got it in that sort of form now, sub in the limits, that would be -1 over p subtract minus 1 over 1, so in other words plus 1. Now as p tends to what it was meant to be, which is infinity, this function here, this minus 1 over p plus 1, think of what's 1 divided by an infinity of many people. One pizza shared by a million people, they get practically nothing each. So that's tending to nothing plus 1, which is 1. So let's just have a quick go with this diagram. What did it look like? It's basically that. And we're saying that this area here will tend to 1. It'll add up to 1. It's a very small area. It'll eventually add up to 1. Infinities obviously can't put infinity on. And the over x squared graph looks like that, but we're not interested in that because there's only 1 to infinity. But it's not the limit this time, it's the area. It'll tend towards 1. Let's have a go with this second one. You might think, what does this curve look like? Well, this curve looks like, put naught in there, you get naught. Infinity, square root of infinity is rather big. End up looking something like that. So we know it's undefined again at the limit infinity. So replace that with a letter. I choose P. And I'm going to call x to the root, x to the half. So that becomes add 1 to the power, divide by the new power. Before I put in the p, I'll just rearrange that so it looks like 2x to 3 over 2 over 3. Put p and 0 in now. So that's just going to give me 2p to the 3 over 2 over 3, subtract nothing. Now, remember last step, as p tends to what it was going to be, replaced it for this thing, which is what we've got here, this, oh, it's done the wrong way around there, 3 over 2 over 3. So a big number times by 2 over 3 to a power is obviously going to be another big number. So that's going to tend to infinity. So we call that one undefined if it tends to infinity. So therefore not defined. But the one we had above that tended to 1 was defined. So pot I was defined. The area of it we could work out as a limit. Your turn now. Have a go at that one. Find, if possible, the value of that. Press pause. Taking it now, you've unpaused and the answer is about to appear. Warning. Did you get that? And if you drew it, see what's going on at the other side. It's tending to the axis, so that area can sort of be defined as 1 over 18. Right, there's an exercise now. Another one for you. So please press pause. Okay, unpaused. Spoiler alert, the answer coming up. That one went to infinity, therefore the integral is said to diverge. It's not defined. Okay, next. We've got more of these, another example for me. So, what's the problem with that one? Well, it's not defined, a text is not, so we're going to have to replace that with the P. And I'm going to call this x to the minus a half. Hope you all follow that. Add 1 to the power, divide by the new power, stick in the limits, make it look nice before we stick in the limits. Then you're just going to get 2 minus 2, and p to the half is root p, isn't it? Right, so as x tends to what it was meant to be, which was 0, as p tends to 0, not x, I think we replace as p tends to 0, 2 minus 2 root p will tend to 2. So that is what my integral area is tending towards. And if I'd had to draw a picture of that, that would have looked have a look on your calculator. Oh, yeah. Anyway, I'm supposed to like that one, and if I draw it on my calculator quickly, not be all day about it then. Oh, it is that thing. It's one of these swooping down here. Anyway, so the area between 0 and 1 would tend to 2. Oops, it obviously would fine up on there. Right. So that, oh no, come on, Kathy. 2. Oops, no, it's 1 in there, 1. That area tends towards 2. This looks a little delight. Is there any problem there? Well, let's rewrite it before we can tell. It's a divide, so we can subtract the indices. That would give me minus 4 over 2, which is the same as minus 2, isn't it? And I've been joined by a hungry cat. Yes, Morris. Right, so integrating that. Oh, no, not integrating that. If I draw the picture of that, what's the problem? Well, that's that graph, isn't it? Let's try it. Let me just check, because I'm notorious for getting it wrong. X to the negative 2. What's the graph look like? Yeah, it's that one. of this sort of graph. So as you can see, there would be a problem at x is 0. Oh, well then you'd say to yourself, well, no problem at all, is there? But can anybody decide what we do with this one? Hopefully one of you said to yourselves we could split this into 2 different integrals. So we could call this, finding this area, we'd have to do it between -2 and 0, where the problem is, and then 0 up to 1. And see if there's any answers for that. So we're splitting this up to now, because it's got the problem with the zeros, we change those for letters. So I'm just going to take the first integral on its own first. So taking them one by one. So I'm going to let that thing, let's work this out first. P minus 2x to minus 2 dx. What will that equal? Well, that will be add 1 to the power, divide by new power. Rearrange it before you put any limits in. What are we doing? I'm an idiot. Minus 1 over p. Take away a negative, so that'll be plus 1 over 2. Now as p tends to 0 here, oh, yuck yuck. So as p tends to 0, what's that say? As p tends to 0, this thing tends to infinity. Because you can't go dividing by 0. It'll be many, many, many. And if that's going to tend to 0, infinity, then there's no point looking at the other bit either, because that will tend to infinity as well. So it all tends to infinity. So because of that, we can just put undefined. So that area there is undefined. Right, on your whiteboard, try that one. Press pause. Have a go. It's a bit like the last one. Okay, hope it's unpaused now. Picture there of that curve, it has an asymptote at 3. So you had to split it from 0 to 3 and 3 to 5 separately and treat them both separately. So get rid of the get rid of the 3 for a p. 0 to p actually turns out to be a number. So that's not put very well there, I don't like that. I like all this, and then I shouldn't have written that. I should have written as p tends to 3, this integral tends to, could write the integral, dx tends to this thing, 0, which is that. And similar with the other strand of that, 3 to 5. Da, 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 da. No, I don't like that. That shouldn't put there. Don't like the way I've done that. So what we say here, as p tends to 3, that gives me this here, which is that. So therefore the limit must be those two values added up, which comes to the final answer there. Right at the bottom of this page it says recall the important results. We just proved this one a bit earlier today with the L'Hopital, and you proved the previous one with Maclaurin some time ago. So we're still doing improper integrals, but it's just that the integration is getting a bit trickier. Right. Well, we know as x tends to infinity, anything of this sort is going to be 0. Just an interesting thing to think of there. Doesn't mean the area is going to be 0, but if you put the top limit in, it would be tending towards 0 there, and therefore a bit of an issue. So we're going to write undefined at x equals infinity, because it's tending to 0. So we replace that with the p. So I've got the integral of p to 0 of x e to the minus x. Now you've probably noticed a little box over here, and there's no relationship between these two functions of x. Therefore we should use parts to integrate. So differentiate the x because of late, which is the log algebra. So differentiate that gives you that. Integrate this, it's going to give me minus e to the minus x, isn't it? So this thing is equal to d for diagonal, and then integrate the 2 on the bottom. So and we're putting 0 to p as our limit, and this thing really should have a square bracket round it with p and 0 on. Okay, integrate that, you're just going to get it again, aren't you? So we've basically got x e to the minus x minus e to the minus x with p and 0 there. Put the limits in. And that just gives me 0, take away 1. Take away 1 will give me plus. Right, so the limit. So as p tends to 0, not well, yeah, 0. No, we're after infinity. Yeah, weren't we? Infinity. As p tends to infinity, this integral tends to infinity. Well, 0 if we think of that, a function to a power, which is p to the 1, e to the minus p, so that's going to tend towards that bit will be 0. This e to the p will just be e to the infinity, which is, oh, it's not a p, is it? It's minus p. My fault there. E to minus infinity. That's going to give us 0 then. And then putting in no, you don't put anything into 1, it's plus 1. So that's tending towards an area of 1. Whiteboard question. Have a go at that yourself. Press pause. Okay, unpause. Here it is. Spoiler alert again. And that where it says use the important result means I've used that thing in the blue box above when I popped in the value of b. As p tends to 0. Yeah. Right. Four questions, multi-choice. Have a go at those ones. Let's see if you understand. And then it'll be the end very soon. So pause, have a go at them, have a good go. Should take about 10 minutes. Bye. Hello. You've now tuned me back in, hopefully unpaused. And the answers coming up. I'm not sure if they are, so I'm going to write them on. Number 1, we should have got C. Number 2, I think that one is D. Then we've got A and D again. Answers in full there if you're not sure what I was up to or you didn't agree with one of those that I just said. Okay, this is your last 5 minutes of the lesson, perhaps. Remembering there's homework questions to do. It says for each of the following improper integrals, find the value of the integration or briefly explain why it doesn't have a value. So have a go at those two and see what you get. Right, so pause the screen. Unpause the screen now, I take it, because here come the answers. That's A, 9/4, and B, oops, maybe not, And there we have B. Hope that makes sense. And if you like to look at the mark scheme. So there's the mark scheme, 8 marks. So that's it from me today. You've got half an hour according to the clock, I reckon, about of time to get on with homework questions that relate to this. However, you have been pausing the video. And on Tuesday we will look at the assessment 3, well, some of it, and I'll need to have a chat with some of you about the odd disaster and see what we're going to do about it. But don't panic now, and we can all celebrate that top of the class was Josh Pratt. He managed to score the highest, so well done, Josh. You can give him a round of applause. Hope you've also done that. And there were some other good results, but also there was the odd not so good. So I shall be chatting to those people on Tuesday about what we're going to do with you, and you probably get a bit of practice time on limits as well on Tuesday. So the sheet that's in your booklet, you maybe want to do that if you think you've done really, really well. You might want to save that for me doing in the lesson. However, it is homework due in on Tuesday, isn't it? So you can't really save some of the homework. But you'll get new homework, so just bear that in mind. There'll always be something to do in that Tuesday lesson, even if you are as done as well as Josh Pratt and got an A star, which, as I say, some of you did. I haven't got my list on me now, but yeah, some of you did really well, some of you not so well. We'll get to that on Tuesday. Alright, take care, have a lovely weekend, and I shall be very happy to see you on Tuesday. Bye.